Now that we have a pretty good understanding of f bracket x modules, let's talk about f bracket x submodules. So here is the question we want to address in this video. What are the f bracket x submodules of an f bracket x module V? Okay, remember how to think about an f bracket x module V. It's a vector space V over the field F together with a linear transformation T from V to V. Where does that linear transformation come from? Well, the action of the polynomial x on the vector space V gives a linear transformation. Okay, so let's take a subset of your vector space, W, a subset of V. If W is an f bracket x submodule, well, that means that it's closed under the action of f bracket x. So that means that for any polynomial p of x in f bracket x, p of x dot w lands back in this vector, in this subset W, where W is any element, little w is an element, and capital W. So in particular, if this is true for all polynomials, it's certainly true for the polynomials of degree 0. So a0 dot w lands back in this subset W for all a0 polynomials of degree 0 in f bracket x, which you can think of as elements of f. So what does that mean? That means that W has to be a subspace of the vector space V. So why is that? Because what is a vector subspace? It's a subset of your vector space that is closed under the scalar multiplication of f and is also itself an additive subgroup. So yeah, so it satisfies all of the vector space axioms. And in particular, that means that the scalar multiplication of f restricted to this subset W has to stay in W. Okay, so now we know that W not only is a subset of V, but it has to be a vector subspace of the vector space V. And what is true about the action of x on a vector W in your vector subspace? Well, this is given by this linear transformation T. So x dot W is this linear transformation that's defining the f bracket x module structure on V applied to this vector W. So x dot W is T of W for all W in your subspace. Okay, so this gets a special name. Let's say that we have a vector space and T, a linear transformation from that vector space to itself, like the situation we're in with this f bracket x module V. If you have a vector subspace U of V such that you apply T to any vector in U and you land back in U, that means that the subspace U is T stable or T invariant. Okay, so you apply T to anything in this subspace and you stay in that subspace. That means that that subspace is T stable or T invariant. So what are we saying here? You apply the linear transformation given by x, this T, to any vector W in your vector subspace, and you stay in this subspace. So that means that if we want W to be an f bracket x submodule, W has to be T stable. But if W is T stable, then even more is true. Then if you take T squared, that is T composed with itself, T squared applied to a vector in your vector space is T following T of that vector. So it's T applied to T of that vector. T of that vector lands back in your vector subspace because your subspace is T stable. You apply T again. It sends things in the subspace to things in the subspace. So you land back in the subspace. So if W is T stable, W is also T squared stable. And for the same reason, it's T to the n stable for any positive integer n. Okay, so now what do we know? We know if we have a subset of our f bracket x module V that is an f bracket x submodule, it has to be a subspace of the vector space V, and it has to be stable under this linear transformation given by the action of x. So is that enough? Like, is that enough to make it an f bracket x submodule? Well, what we really need is that it has to be closed under the action of any polynomial p of x in f bracket x. So what is p of x dot w for some vector in our vector subspace? Well, p of x, let's use the notation from earlier in this lecture, an x to the n plus 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 a1x plus a0. This is an acting on t to the n of w plus 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 a1 dot t of w plus a0 dot w. And every one of these terms is in w because w is t stable, t squared stable, t to the n stable. So all these t to the n's applied to w, these all land back in w. And then w is a vector subspace. So the scalar multiplication, ai dot some vector in w stays in w. And now we're adding together a bunch of vectors in this vector space w. We stay in that vector space. So this vector is always in w. And what that means is that the f bracket x submodules of v are precisely the t-stable subspaces of v. That if you have w inside of v, a vector subspace, and it's t-stable, that means that it's closed under the action of f bracket x, so it is an f bracket x submodule. So to say this in a slightly different way, like we said for the correspondence between v being an f bracket x submodule to v being a vector space over f together with a linear transformation, for submodules, we can say w is an f bracket x submodule of the f bracket x module v if and only if w is a vector subspace of v and w is a t-stable subspace, where t is this linear transformation that is the one giving the f bracket x module structure on v. Okay, so I'll pause and erase, and then I'll give you an example that refers back to something that we talked about earlier in this lecture. Let's talk about an example that builds on something we spoke about earlier in this lecture. Let's take our vector space v over f to be f to the n, the affine n space. And let's take our linear transformation to be the shift operator. So for each k between 0 and n, we can define uk to be the set of all things in v that are of the form x1 up through xk, and then a bunch of zeros, where each of these xi's can be any element in the field. So what is the thing that defines uk is you can be anything in the first k spots, and then zeros between spots k plus 1 and n. Okay, it's clear that this is a vector subspace. I mean, you can check it. It looks just like not an affine n space, but affine k space. And you can check that this really is true. And this is t-stable. When you apply the shift operator, the non-zero things just move to the left. So you're not going to take something in uk and end with something out of uk because it has a non-zero entry in one of the things at the end. So this is clearly t-stable. So it's a vector subspace of v that is t-stable. So it is an f bracket x submodule of v. Okay, so the last thing I want to talk about in this lecture involves giving one of the new big definitions that'll be really important for the next few lectures. So let's say that R is a ring and M and N are R modules. A map phi from M to N is an R module homomorphism if phi of x plus y equals phi of x plus phi of y for all x and y in M. M and N are both abelian groups. This has to be a homomorphism of these underlying abelian groups. And it needs to behave nicely with respect to the action of R on M. So phi of R dot M has to be R dot phi of x. Sorry, phi of R dot x equals R dot phi of x for any x in M and R in the ring. So this homomorphism, this map, needs to respect the action of R on M and on N. Okay, we'll talk a lot more about R module homomorphisms in the next lecture and the one after. For now, one thing I want to focus on is an R module homomorphism is an isomorphism or an isomorphism of R modules if it's an R module homomorphism that's also surjective and injective. Okay, so now that we understand what an R module isomorphism is, we can ask, when are two f bracket x modules isomorphic? Why am I asking this question now? Because this question is motivation for a lot of the linear algebra that we're going to talk about at the end of this course. So remember, an f bracket x module is a vector space V over F together with a linear transformation T from V to itself. It's going to be a while before we answer this question. It'll actually be probably one of the very last things in this course. In section 11.2, which is called the matrix of a linear transformation, we're going to see how to start with this linear transformation T from V to itself and output a matrix that represents that linear transformation. So, okay, when you took linear algebra, this is probably something that you saw just for V being R to the N for some N and R being the real numbers. All right, so what does that mean? How are we going to ask this question? Well, if you start with two f bracket x modules, let's say V1, some vector space over F, together with this linear transformation T1 from V1 to itself, and then V2, some other vector space over F, together with this linear transformation T2 from V2 to itself. The material of this discussion of the matrix of a linear transformation is going to give us one matrix for each of these transformations. So we'll get two matrices. They'll both have entries in F. Let's call them A and B. So the matrix of the first linear transformation, the matrix of the second linear transformation. All right, so now there's this question. You start with two f bracket x modules. You get two matrices. So what is the thing about these two matrices that answers this question? What is the thing about A and B that says whether or not the corresponding f bracket x modules are isomorphic? And that is something that we'll talk about in section 12.2 in this chapter on the classification of modules over a PID. F bracket x, we know, is Euclidean domain, so it's an example of a PID. Section 12.2 is about the rational canonical form. And in particular, if you want to skip ahead and see where this is going, theorem 15 gives a nice answer to this question.